Welcome to another installment of Advanced Chemistry Lectures. Today's lecture will be an extension of a previous lecture on electron counting of transition metal complexes. In this lecture, this tutorial, I will focus on the 18 electron rule. And so many of you may have noticed that as we are electron counting transition metal compounds, 18 electrons seems to come up a lot. And so what is the basis of this so-called 18 electron rule? And so many chemists kind of oversimplify this and kind of point to this as the transition metal complex extension of the octet rule. And so if we take a molecule that you're very familiar with, methane, as you know, methane, carbon has 4 valence electrons. Each hydrogen has 1 valence electron. And when they form methane, you get an sp3 hybridized carbon center that now carbon has a full valence octet. And so this octet represents the noble gas configuration of neon. And so this is said to impart a certain stability to methane. And so the extension of this is that once we get to transition metal complexes, like this cobalt 3 plus transition metal complex, which is an 18 electron compound, now that you've introduced d orbitals, you have 5 d orbitals, they can each accommodate 2 electrons, and so that adds 10 more electrons to your total count. That you should get to 18 valence electrons, and then this should have a stability associated with krypton and therefore be more stable. Well, we know that cobalt 3 is not in fact D10, so what actually is going on here? And so the first thing you have to know how to do is actually electron count transition metal complexes, and I urge you to go back and look at my previous lecture. But what we're going to do is we're going to treat all the ammonias as Lewis bases, and so give them their electrons back. And when you give them their electrons back because they are the Lewis base, you end up with cobalt 3 plus, which is a D6 transition metal complex, and ammonia, which is a neutral 2 electron donor. You have 6 of them. If they each contribute 2 electrons, that is then 6 electrons due to the metal center, 12 electrons due to the ammonia, for 18 electrons overall. And so why is this particularly stable? Well, what we really need to do is look at the molecular orbitals. And so if we treat our cobalt 3 hexamine complex shown here, which we know is an 18 electron complex, it also has octahedral symmetry. And so if you're going to build a molecular orbital diagram, what you need to do is focus on the valence shell. And so on the left side here, I have a 3d, 4s, and 4p orbitals corresponding to the valence orbitals on the cobalt center. And on the right side, I have let's say the ligand group orbitals that can form sigma bonds with the transition metal center. And so what you have to realize is that the symmetry labels of the individual orbitals shown on the left side can be obtained from a OH character table in the back of your textbook. A lot of effort actually goes into finding the symmetry of the ligand group orbitals that can form sigma bonds. It's a little bit outside of the scope of what we're addressing here, but what you need to really recognize is the fact that if you have symmetry labels that appear on both sides, let's say the EG, the A1G, and the T1U, what this means is that they can then form bonding and anti-bonding combinations. If there's 3 such labels, let's say if you had 2 A1Gs on the left side and 1 A1G on the right side, you would form largely a bonding, non-bonding, and anti-bonding combination. And so what orbitals localized on the metal can actually overlap with the sigma-based ligand donor orbitals on the right side. And so what you should really want to do is think about what the actual orbitals on the transition metal center look like. And so they look like this. And so you have 5 d orbitals. 2 of them have EG symmetry and can form sigma bonds with the corresponding ligand donors, and those are the dz squared and dx squared minus y squared orbitals. Note that those orbitals are directly aligned along the bonding axes that the ligands are actually going to form in an octahedral compound. Notice that an s orbital could also form a sigma bond with ligand donor orbitals, and the p orbitals are perfectly aligned to form bonds with the corresponding ammonia ligands as well. And so these have the EG, A1G, and T1U symmetries we need. And so when you now build the MO diagram, you get 6 bonding pairs down here corresponding to the 6 sigma bonds of this cobalt 3 complex. You then have these T2G orbitals, which are kind of in the gaps, as I would call them. And what I mean by in the gaps is that the lobes of those corresponding d orbitals do not align along the bonding axes, and these remain as the T2G non-bonding set. And so your 6 d orbitals of the cobalt center then appear there, and you end up with an 18 electron compound. 6 sigma bonds giving you 12 electrons, plus 6 d electrons largely localized on the metal center, giving you these extra 6 electrons you need to get to the total electron count of 18. Well, if you're kind of thinking ahead, you may say, well, you just chose cobalt 3 because it's D6. 12 plus 6 give you 18 electrons. What if you don't have a D6 transition metal center? And that's a really good thought, because it turns out that transition metal complexes of the first row don't really obey the 18 electron rule. And in fact, in this very nice paper from the Journal of Chemical Education in 1969, argues that there is actually 3 types of transition metal complexes. A group in which the electron configuration are completely unrelated to the 18 electron rule. These are the first row transition metal complexes. A group of complexes which follow the rule, at least insofar as they never have more than 18 electrons. And the third group in which the complexes rigorously conform to the rule. And so if we look at our little table we have here, notice that the cobalt compound I chose is in fact the 18 electron compound. But if we go to the opposite ends of the spectrum, this titanium compound is stable with only 12 electrons, and this zinc compound is stable with 22 total electrons. And so if we go back to our MO picture and we look at it, notice that the titanium compound again is 12 electrons. This is a titanium 4 center. Each fluoride is -1. The complex is 2- overall, so it must be titanium 4, which is D0. And so the molecular orbital diagram will look exactly like this. There are no d electrons to place in this T2G subset. Notice if we go to the zinc compound, all of the ethylene diamine donors are neutral, and so this is zinc 2+. Zinc 2+ is D10, and so if we were to populate this molecular orbital diagram, the T2G set would be full, in addition to the EG star subset. And so we would now have our D10 would populate the T2G and the EG star. And so here you're putting electrons now into anti-bonding orbitals. So why is this zinc complex stable? Well, this zinc complex is stable because it's a first row transition metal complex. This delta O gap, which is a measure of the energy difference between the T2G and EG star subsets, is small. And so what that means is that by putting electrons into this anti-bonding orbitals, there's actually not so much of an energetic cost. It's not that bad. And so if it's not that bad, it's okay to put electrons there. And it turns out that this zinc 2+ complex is in fact stable with a 22 electron count. So if this delta O gap matters so much, then, and you need to actually think about whether you want to populate it or not, what you really want to think about is, well, how can you dictate this delta O gap? How can you make it bigger, or how can you make it smaller? And if we take 3 isoelectronic transition metal complexes, the cobalt 3 complex we've talked about already, the rhodium complex that appears one below it, and the iridium complex that appears one below that, it appears that the delta O gap, in fact, gets very large as you move down the transition metal series. And so this delta O gap is really a measurement of taking electrons localized in the T2G subset and promoting it to EG star subset. And so what you can see is that if you had iridium really has, let's say, an EG star subset way up here, and it requires a large amount of energy, a large jump, to populate that anti-bonding subset. And so the question is why? Well, when you look at this, we know that the EG star subset is in fact anti-bonding. And so what we really need to consider is the other half of this. Remember that we have ligand donor orbitals that have matching symmetry here. Now the EG subsets have matching symmetry, and so they form a bonding combination, which is down here, and then an anti-bonding combination, which is up here. And so when we're at cobalt 3+, its orbitals look something like down here on the lower left. And so the 3D subshell is actually really tightly held to the nucleus. And in fact, its distance doesn't really stretch that much farther than the 3p subset. And so the overlap between the ligand orbitals and the transition metal and the d orbitals on the transition metal center are really poor. And so if they're really poor, the bonding combination is not that great. If the bonding combination is not that great, and I mean bonding combination I'm talking here, is not that great, then the anti-bonding combination will not be so bad either. However, if you have iridium, in the case of iridium, the 5D subshell is really expansive. It extends very far away from the nucleus. And the fact that the d orbitals on the iridium center extend very far from the nucleus means that they overlap really well with the incoming ligand orbitals. The function of this is that now your bonding combination is really, really good. If the bonding combination is really, really good, it gets dragged down in energy. What that means is the opposite end of the coin, the anti-bonding combination is really, really bad. And so the EG star subset gets raised in energy. And so now the effect of that is that the delta O gap is really large. It requires a large amount of energy to promote electrons from the T2G subset into the EG star subset. And so this kind of brings us to the second class of transition metal complexes, those that never, ever have more than 18 electrons. And these are largely second and third row transition metal complexes. And so if we think about the iridium compound we just discussed, which is shown here, remember that 12 electrons are counted for the 6 sigma bonds from the iridium to the ammonia centers. And so then the D6, iridium 3 D6, the 6d electrons now populate the T2G. If you were to have a 7th d electron, it would go into the EG star subset, which is rigorously anti-bonding. That's really bad. That's going to weaken the bonds considerably. That's going to give you a 19th electron. That also does not happen. And so second and third row transition metal complexes typically never have more than 18 total electrons. And so you may not believe me. So why is this delta O gap so large? And so do you have any examples of exactly how this plays out in the real world? And in fact, there's a really nice case of the iron BiPi 3 times and ruthenium BiPi 3 times actually showcasing how this delta O gap gets really, really big as you move from the first row transition metal complexes to the second and third row. And so ruthenium BiPi 3 times 2+ is a transition-based chromophore. And in fact, there's related analogs, all of which are low-spin D6 complexes of the second and third row. And these are all chromophores, and they all have applications in artificial photosynthesis, OLEDs, and making digital displays, and photocatalysis. But ruthenium is one of the rarest elements on Earth. And so iron would be the perfect alternative. And why would iron be the perfect alternative? It's right above ruthenium in the periodic table. It also has a low spin T2G ground state. And so how can this ruthenium center actually act as a chromophore? Well, what happens is the ruthenium center is hit with light. You then have electrons that are localized on the ruthenium center. What occurs is a metal to ligand charge transfer. A metal to ligand charge transfer in which the electron is promoted from ruthenium into the pi star orbitals on bipyridine. This creates a radical anion. At the same time a radical anion is created on the ligands, the ruthenium center is formally oxidized to the 3+ oxidation state. And so it's really very simple essentially photophysics going on. And so why doesn't the iron center engage in this type of behavior? Well, the iron center does not engage in this type of behavior because its delta O gap is too small. So what happens? Well, if you take this iron center and you do the exact same thing, you hit it with light, what you end up obtaining is just essentially a high spin transition metal complex. The lowest energy excited state is just the 5T2 state. The 5 represents that you have a quintet state. A quintet state means you have 4 unpaired electrons as shown here. And this has been verified by the bond elongation that's observed in these high spin compounds of approximately 0.2 angstroms. Why do the bonds elongate? Well, you're putting electrons into anti-bonding orbitals. If you're putting electrons into anti-bonding orbitals, that's going to weaken bonds and subsequently elongate them. And so since this delta O gap is so small and the pi star orbitals located on BiPi are so high in energy, this does not engage in the same type of metal to ligand charge transfer behavior. And so in the case of ruthenium, this gap now is so big again, and remember this gap is so big. This gap is so big because the bonds, the ruthenium nitrogen bonds are so good that the anti-bonds are so bad. Well, this gap again is so big, and so the bipyridine-based orbitals highlighted here in the blue box are actually much lower in energy. Electrons then can be promoted from the T2G state into the pi star orbitals localized on the bipyridine ligand. You actually get an excited state singlet, but due to very efficient inter-system crossing, you end up getting a triplet excited state that's responsible for the luminescence. And so this is definitive evidence then that as you go from the first row to the second row, that the delta O gap does increase. And this is extremely important. And this is extremely important because transition metal complexes of the first row are completely unrelated to the 18 electron rule. Due to this small delta O gap, there's very little energetic cost in populating the anti-bonding orbitals. On the other hand, second and third row transition metal complexes are type 2 transition metal complexes that never have more than 18 electrons, and they never have more than 18 electrons because that 19th electron would go into a rigorously antibonding Eg star subset. There's a huge energetic cost associated with this, and therefore it does not happen. This then brings us to the type 3 compounds, those that rigorously conform to the rule. And if we look at this table that I stole from this Journal of Chemical Education paper, notice that all of the transition metal complexes, minus the one I'm crossing out right now, all have pi acceptors. When you have pi acceptors, you typically rigorously adhere to the 18 electron rule. The rule is actually the rule. And so why is that? Well, what do pi acceptors do? And so we haven't talked about the pi acceptor interaction yet. What we've really talked about is only the sigma bond. And so as you know, carbon monoxide has a Lewis structure that looks like this, a formal negative charge on carbon, a formal positive charge on oxygen, and the lone pairs on carbon now act as a Lewis base towards the transition metal center, donating to a sigma acceptor orbital. I've drawn it here as a dz squared orbital. But more importantly, CO also can accept electron density back from the transition metal center. And so how does that happen? Well, the metal orbitals with d pi symmetry can actually donate electron density, as shown by the green arrows, into the pi star orbital on CO. And for every CO, there's 2 of these interactions. And so if you have 6 CO ligands, shown here, if you have 6 CO ligands, there's 2 of these interactions per CO. You now have 12 total, essentially, orbitals that now can participate in bonding with the transition metal center. And so what does the second pi acceptor interaction look like? It's hard to draw, and so I wasn't able to draw it with ChemDraw. I'm going to draw it here. It's actually in and out of the plane of the computer screen. You have the pi star orbital on CO. Again, remember, this is the pi star orbital. The phases are out of phase with one another. And then you have a metal d pi orbital. And so again, this is supposed to be drawn in and out of the page. You have a metal orbital with d pi symmetry, able to donate electron density to the pi star orbital localized on CO. And so now how does this actually affect our molecular orbital diagram? Well, if we look at our molecular orbital diagram that only considers sigma bonding, we have a chromium 0 D6 18 electron compound. Remember, these are the 6 sigma bonds that are shown here, equaling 12 electrons. Chromium 0 is D6. Here are its 6 d electrons localized in what is a non-bonding T2G set. But remember, now we have pi star orbitals. We have this flow of electron density from metal d pi orbitals into the pi star orbitals on CO. And so these T2G set, which was non-bonding, has the proper symmetry to overlap with the anti-bonding orbitals on CO. And so if we now kind of expand our diagram to include that, we now, again, remember we had 6 COs. There's 2 essentially pi back bonding interactions possible. That contributes 12 new orbitals. Well, of these 12 new orbitals, notice that 3 of them have T2G symmetry. And so now we get a bonding combination and an anti-bonding combination between these orbitals. What the result of that is that the T2G set now becomes bonding. What that results in now is a large delta O gap. When that delta O gap is large, compounds want to be low spin. And furthermore, now electrons 13 through 18 are now more stabilized. You now have a compound that rigorously adheres to the 18 electron rule. And so one thing you may have noticed is that I've kind of neglected the fact that square planar compounds exist. Well, remember, square planar compounds are typically second and third row transition metals that are D8. And so if they're D8, they're also usually 16 electrons. And so how does this actually work itself in with the 18 electron rule? We saw here previously that second and third row transition metal complexes like this iridium compound here never really can have more than 6 d electrons, because you'd be putting a 7th d electron into the anti-bonding orbital. But now with square planar compounds, they're typically D8. So what gives? Well, what gives is that these square planar compounds like Wilkinson's catalyst shown here, if we actually now analyze it from a molecular orbital perspective, it looks like this. And so again, these ligand donor orbitals with A1G, B1G, and EU symmetry, a lot of math goes into deriving these labels, which we're not going to talk about here. But if we go to the character table and we actually look up what the symmetries of the corresponding d orbitals, s orbitals, and p orbitals are, we can now build the MO diagram forming bonding, non-bonding, and anti-bonding combinations. And so when you think about a square planar compound like Wilkinson's catalyst, you want to think about what d orbitals can actually lead to sigma bonds. And you can see that the B1G set here, which is derived from the dx squared minus y squared orbital, is directly in line with the ligands that bind to the transition metal center. Furthermore, you can imagine the py and px orbitals also overlapping very nicely with the incoming ligand the lone pairs localized on the ligand donors, and an s orbital could also do that. There's some mixing of character between the dz squared and the 5s orbital shown here. There's some mixing, and so the fact that there's some mixing, they have the same symmetry labels, means you get a very nice bonding combination shown here. And so the 4 sigma bonds are now shown at the bottom third of the molecular orbital diagram. There are 3 d orbitals that are still rigorously non-bonding. Those are the doubly degenerate dyz and dxz orbitals, the B2g orbital, which is the dxy orbital. And then notice that the A1g orbital here, which is largely the dz squared orbital, also sits rather non-bonding. Notice again, you have an A1g on the right side, an A1G on the left, and a second A1G on the left. That is 3 A1Gs. You typically get a very bonding orbital, a mostly non-bonding orbital, and then a rigorously anti-bonding orbital. Rigorously anti-bonding orbital shown here. And so why does this lead to square planar rhodium-1 D8 compounds being 16 electrons rather than 18 electrons? Well, let's look at the MO diagram, particularly this area shown right here. Well, if we look at that particular area, the first thing to know is that the A1G orbital is largely dz squared, and it's largely non-bonding in nature. And so it's the orbital that extends above and below the plane of the square planar molecule. It's kind of just hanging out. Furthermore, the rhodium center, which has 4d orbitals, overlap very well with the ligand-based orbitals. That results in a B1G star that is rigorously anti-bonding, and you do not want to put electrons there. Furthermore, if you think about it, I'm going to draw it here on the rhodium center. If you have the PZ orbital, which is largely non-bonding, in order for the ligand to donate to that orbital, this would give you the 17th and 18th electrons. Well, that orbital is extremely high in energy. If that orbital is extremely high in energy, then it's really not going to play ball. And so these square planar compounds are typically very happy having 16 electrons. Well, what you also might notice is that you may have other geometries, particularly trigonobipyramidal transition metal complexes, like the ones highlighted here. And what you'll notice here is you can get variable electron counts. Very often, trigonobipyramidal transition metal complexes are 18 electrons, but they don't have to be. This iron compound right here is trigonobipyramidal, and it's a 16 electron compound. And so from a molecular orbital perspective, how can we explain that? Well, just like we've been doing, here are your 5 ligand donor orbitals with their corresponding symmetries. They form 5 bonding combinations. Notice that you have an A1 prime and A1 prime. Here's an A1 prime. Here's an A1 prime. You have an A2 double prime. Here's an A2 double prime. And you have an E prime. Here's an E prime. Here's an E prime. And so notice that you have now 3 E primes, and so you actually have 4 A1 primes. And so you're getting very, very bonding. You're getting sort of non-bondings, and you're getting very anti-bondings. But the bottom line is that you form 5 sigma bonds shown here. This corresponds to the first 10 electrons. Well, notice that the E double prime subset, which corresponds to the DYZ and DXZ orbitals, they're really not going to overlap with any of the ligand-based orbitals that approach the iron center, and so they remain rigorously non-bonding, NB, non-bonding. Well, the overlap between the E prime sets is really not so good. We have a iron, which is 3D, and so the bonding combination is not so great, and so the anti-bonding combination, that means, is not really all that bad. And so this E prime is really largely more, I'm going to call it non-bonding, even though there is some anti-bonding character. Furthermore, again, because it is the iron center and it is a 3D metal, the A1 combination here, which really is, if you notice, you have 4 different A1 prime labels. And so the fact that you have 4 A1 prime labels, 2 of them are down here representing bonding orbitals. This then is anti-bonding, but it's not too anti-bonding. It's nothing like the anti-bonding set that's up here. And so this orbital right here is also still in play. But if we consider this iron center, which is iron 0, it is D8. That means that these orbitals are now going to be fully populated. The energetic cost associated with populating this E prime is not so bad, and therefore this iron 0 D8 18 electron compound is pretty stable. Again, these two levels are filled. If it's D8, the E prime is mostly non-bonding, even though there is some anti-bonding character. The E double prime is rigorously non-bonding. But what's really important is that this A1 prime subset right here is really not that anti-bonding due to the poor overlap between the 3D and the incoming ligand orbitals. And in fact, this 3- cuprate anion is in fact stable, and it is a 19 electron compound. It is D9, and so the 9th electron actually populates that A1 prime that is somewhat anti-bonding. And so the punchline is that 18 electrons is pretty common, but it can vary across the map. Well, what about tetrahedral compounds? Many transition metal complexes are tetrahedral, and before we kind of approach what the molecular orbital diagram of this looks like, I think it's really instructive to consider or think about a tetrahedral compound in three-dimensional space. And kind of the best way to think about it is to put it on the opposite corners of a cube. And so here we have nickel tetracarbonyl, a horribly toxic transition metal compound. And what's kind of a hallmark of tetrahedral transition metal complexes is S4 axis. And so how do we explain this S4 axis? Well, this S4 axis is a C4 followed by a perpendicular reflection about a mirror plane. And so how can we use this now tetrahedral geometry within this cube to explain this? Well, the C4 axis is along the Z axis, and so this sphere is going to go to this position, this sphere is going to go to this position, this sphere is going to go to this position, and this sphere is going to go to this position, represented a rotation of 90 degrees. Well, what about the horizontal mirror plane? Well, this is the Z-axis in which we had that C4. Well, the horizontal mirror plane is now right here, and so 2 is going to end up here, 1 is going to end up here, 3 is going to end up here, and 4 is going to be reflected to this position. Notice that we get back exactly with what we started with. This is the S4 axis of a tetrahedral transition metal complex. And the second thing you kind of want to think about is like, how are we going to orient the axes to explain the bonding? And so if we look at the d orbitals, what you may realize is that the dz squared and dx squared minus y squared are going to be non-bonding in this case. Notice that this is the z-axis, and so the lobes of the dz squared orbital are going to extend through the top and the bottoms of the cube, not overlapping at all with the ligands on the carbon monoxide. The dx squared minus y squared are going to come right out the faces in the front and in the back. It's going to be hard now to draw, but also out the sides. And so they do not overlap at all with the CO ligands, which are at the corners of the cube. However, this set of triply degenerate orbitals overlaps a little bit better. And so when we build this MO diagram, again, we're going to have our 4 ligand donors with the corresponding symmetries shown here. We now have our E subset, which is rigorously non-bonding, our T2 subset, which bonds a little bit better, not all that good. And so we get our 4 sigma bonds shown here, and our E subset remains now rigorously non-bonding. And what is extremely important is that this delta, what used to be called the delta O gap, it's now called the delta T gap because it's tetrahedral, is always really small. And it's in fact approximated based on the angular overlap method to be about 4/9 the size of the octahedral gap. And so this is why tetrahedral transition metal complexes are typically high spin. So if you had a high spin D5 system, it would typically be populated in this fashion. And that's due to the fact that this delta T gap is so small. And so now if we're thinking about the 18 electron rule, how does nickel tetracarbonyl adhere to this 18 electron rule? Well, it's nickel 0, which is D10. So it's 10 d electrons go into this position. 4 of the electrons go into the rigorously non-bonding E set, and then the remaining 6 electrons go into the somewhat anti-bonding but really pretty non-bonding T2 set. Remember here we have T2 here, T2 here, and T2 here. This then gives us very bonding orbitals, mostly non-bonding orbitals, and then rigorously anti-bonding orbitals. And so that is why tetrahedral compounds typically kind of span the electron count really widely, because this T2 set is not really all that anti-bonding. And so if we look at this cobalt compound that's going to flash up in a second, you're going to see that this T2 set is not going to be fully occupied. It's actually going to have 3 electrons. This cobalt 2 compound is D7, so the first 4 d electrons go in this position, and the remaining 3 electrons go in this position. It's actually high spin, so it's going to go 1, 2, 3, 4, 5, 6, 7, but nonetheless 3 electrons appear in the T2 set. The T2 set, again, is not all that bad. It's mostly non-bonding in nature. And so tetrahedral compounds, unlike some of the ones we've talked about, error electron counts kind of span all over the map. And so what I've hoped to convince you here is that the 18 electron rule is really a pretty breakable rule, my favorite types of rule, really. And transition metal complexes typically, especially octahedral ones, fall into 3 classes. A group in which the electron configurations are completely unrelated to the 18 electron rule, which is largely defined by first row transition metals due to their small delta O gap, and so there's not really an energetic cost in populating the EG star subset. This is exactly opposite to second and third row transition metals, especially the ones that are octahedral. Those never have more than 18 electrons because the delta O gap is so large. The EG star subset then is rigorously anti-bonding. You do not want to put any electrons there, and therefore the compounds never have more than 18 electrons. However, this ruthenium 2+ compound right here is D6, and so what you know is that many second and third row transition metal compounds are square planar, and they're D8, and so what they end up doing is adopting a different geometry, most typically square planar. And I showed you from a molecular orbital perspective why 16 electrons is sort of the golden rule for square planar transition metal complexes. And then the third type here is those that rigorously adhere to the rule. Ones that rigorously adhere to the rule typically have pi acceptors as ligands, and the reason for this is that a T2G set becomes very bonding. That stabilizes the overall electron count, and those are rigorously adhering to the rule. And then I also obviously talked about other geometries and how the molecular orbital approach can lead you to get electron counts that kind of can span a number of different total electron counts. Trigonal bipyramidal, very often you see 16, very often you see 18, but you can even see more than 18 electrons because the anti-bonding orbitals are not so bad. Tetrahedral compounds are all over the map as well. And so the punchline is that the 18 electron rule is really a pretty breakable rule. And so I hope you learned something, and goodbye.